Now let us discuss about the physical properties of carboxylic acids. Physical properties of carboxylic acids. Now the first is the boiling point. Amongst all organic compounds in your syllabus in class 12th, the boiling point order is this. This is a hydrocarbon, then we have a haloalkanes, then we have ethers, aldehyde and ketones. Now hydrocarbons have the lowest boiling point. They have only the weak van der Waals forces present. Only weak van der Waals forces present. So that's why the hydrocarbons have the lowest boiling point. Now haloalkanes, ethers, aldehyde and ketones, they have a dipole-dipole interactions. So the intermolecular forces are the dipole-dipole interactions, and these are stronger than van der Waals forces but weaker than the hydrogen bonding present in amines, alcohols and carboxylic acids. Carboxylic acids. Now these three compounds, they have intermolecular hydrogen bonding. Intermolecular hydrogen bonding. So acids have the highest boiling point. It means carboxylic acids are highly associated via extensive network of hydrogen bonding. So carboxylic acids have a extensive network of hydrogen bonding. Extensive network of hydrogen bonding. Now next we will discuss about the acidic strength of carboxylic acids. Acidic strength. Now carboxylic acids are acidic in nature. They ionize in water to give the H plus ion, and this is called the conjugate base of carboxylic acid, and this is the H plus ion form, and the equilibrium constant for this reaction is called the acid dissociation constant, and that is equal to the conjugate base concentration into H plus ion concentration divided by the acid concentration. So whenever you have to write the expression for the dissociation constant, you write this way: H plus ion, conjugate base, these two are in the numerator, and carboxylic acid in the denominator. Now this acidic strength means the ease with which the compound can release H plus ion. So acidic strength is directly proportional to Ka value. So higher the Ka value, stronger the acid is. Inversely proportional to the pKa value, where pKa is defined as the minus log of Ka. So higher the pKa, weaker the acid is. Is directly proportional to the stability of the conjugate base. Stability of the conjugate base. So more the stability of the conjugate base, stronger the acid is. And inversely proportional to the electron density around hydrogen of the carboxylic acid group. Now first point, we'll compare the acidic strength of the formic acid and acetic acid. Now this is formic acid and this is acetic acid, and remember this methyl group is electron donating group and increases the electron density around hydrogen atom. So methyl group is electron donating group, increases the electron density around hydrogen atom. So difficult to remove hydrogen as a H plus ion. Difficult to remove hydrogen as H plus ion, and hence CH3 COOH is a weaker acid than formic acid, and hence acetic acid has a lower value of the Ka than formic acid, or we can say the conjugate base of acetic acid is less stable as compared to the conjugate base of formic acid. Now the second point is the presence of electronegative atom. Presence of electronegative atom. Now electronegative atom is the atom more electronegative than carbon. Now this electronegative atom exerts an electron withdrawing effect. Electron withdrawing effect, and therefore the electronegative atom decreases the electron density around hydrogen atom, around hydrogen of the carboxylic acid group. So the removal of hydrogen as a H plus ion becomes easier. Removal of hydrogen as a H plus ion becomes easier, and the acidic strength increases. Acidic strength increases. So the haloacetic acid is a stronger acid than acetic acid. Now the third point is the electronegativity of halogen. Electronegativity of halogen. Now as the electronegativity of X increases, X means halogen, from iodine to bromine to chlorine to fluorine. So as the electronegativity of X increases, electron withdrawing power of X increases, removal of hydrogen as H plus ion becomes easier, hence the acidic strength increases. So fluoroacetic acid is stronger than chloroacetic acid, is stronger than the bromoacetic acid. The fourth point is the number of electronegative atoms. Number of electronegative atoms. Now as the number of electronegative atoms increases, removal of hydrogen as H plus ion from the COOH group becomes easier, and the acidic strength increases. Acidic strength increases. That's why this dichloroacetic acid is stronger than the chloroacetic acid, stronger than acetic acid. Now the fifth point is the distance between the electronegative atom and the carboxylic acid group. Now as the distance between the electronegative atom and the carboxylic acid group increases, electron withdrawing power of X decreases. Electron withdrawing power of X, any electronegative atom, electron withdrawing power of X decreases, and the removal of hydrogen as H plus ion becomes difficult, and the acidic strength decreases. And the acidic strength decreases. That's why this is called the beta chloropropanoic acid. Your chlorine is at the beta position, is a weaker acid than the alpha chloropropanoic acid. So beta chloropropanoic acid is weaker acid than the alpha chloropropanoic acid. In this case, the chlorine is at the alpha position, has a stronger minus I effect, stronger electron withdrawing power. The next is number 6 point is we'll compare the acidic strength of benzoic acid and acetic acid. This is benzoic acid. Now in this case, this alpha carbon is sp2 hybridized, has a 33% S character. And in acetic acid, this alpha carbon is sp3 hybridized and has a 25% S character. And as you know, more the S character, more the percentage S character, more the electronegativity of carbon atom. So more the electron withdrawing power, more the electron withdrawing power, and more the acidic strength. And more the acidic strength. So benzoic acid is stronger than acetic acid. The next point is electron withdrawing group increases the acidic strength of benzoic acid, like nitro group, acidic strength, and electron donating group like methyl group decreases the acidic strength of benzoic acid. Acidic strength of benzoic acid. Therefore, this 4-nitrobenzoic acid is stronger than benzoic acid, stronger than 4-methylbenzoic acid. The next point is that all ortho-substituted benzoic acids are stronger acid than benzoic acid. Stronger acids than benzoic. And this is known as the ortho effect. This is basically the steric effect, crowding effect. So because of the crowding, the ortho isomer gives away H plus and more easily. That's why this ortho-nitrobenzoic acid is stronger than ortho-methylbenzoic acid, stronger than benzoic acid. And the last point is that benzoic acid is stronger than phenol, is a stronger acid than phenol. Benzoic acid is stronger acid than phenol. The reason is that the conjugate base of benzoic acid, called benzoate ion, has two equivalent resonating structures, resonating structures with the negative charge on the more electronegative oxygen atom. So the conjugate base of benzoic acid is more stable than the conjugate base of phenol, and conjugate base of phenol is called the phenoxide ion, and hence benzoic acid is stronger than phenol, a stronger acid than phenol. So this is all about the physical properties of carboxylic acid, and the important is the acidic strength. So just revise these examples. These are very important from the examination point of view.